Welcome, everybody. Nice to see still some people ready to listen to more exploits today. So I will talk about Google Nest Wi-Fi Pro, and let's start with that. That's how it looks like, and that's what it is. So it's a Google device. The Nest team from Google makes various devices. They released this one somewhere in November 2022. It's based on Qualcomm SoC, and it has Android and some secure boot features. There is no known debug shell or user shell on the device, so it's just a device you get, plug in, and it works, and that's it. And exactly 1 year ago, here, in The Hague, at Hardphone, Google came with engineers to introduce the devices and have them as targets for Hardphone competition. A friend of mine made this picture showing how I looked at it, and that represents it well. So I definitely wanted to check it out and see how the Google Nest works. So I started with that, started to investigate what the good attack paths are. Of course, it's a router. You have the standard network. You might want to try to attack some interfaces on the LAN interface, maybe the internet connection, or some Wi-Fi parts. Or you can focus on the physical paths, like, all your attackers who break into your house and start desoldering chips from your routers. And of course, that's what we did because it's Hardphone at hardwear.io. So that was also in scope, which is very nice for this competition from Google to also introduce physical attacks to the devices. So that was the attack path I took. So if we take it apart, it's quite a big board inside with very big heatsinks all around it. And it has various components in it. So we can take a look a little bit closer. So on one side, there is a Qualcomm Wi-Fi chip. It's not the main SoC, it's another Qualcomm chip. There you have multiple of those for different bands. They have the DDR, they have the Nordic BLE chip on that side. And on the opposite one, there is the main SoC, that's Qualcomm IPQ 5018. And the eMMC chip next to it, you see it highlighted in green. And at the bottom, you can see there is an unpopulated debug port. It also, on the plastic case, there is an opening for it. So they clearly use it for some debugging, and it's definitely a good target to start with when you do hardware reversing. So yeah, there is 2 mystery pads, 2 ground pads, and there is a UART RxTX. So, of course, I was hopeful to expect root shell right there and be done with it. There is no root shell, but there is some messages printed. So when the device starts, it prints the early boot logs. It goes into first few boot stages. And then when the Android kernel starts, it stops printing. So there's no more information to the attacker, unfortunately. But that's already a good start. So we can see how the device boots and what kind of code executes on the device. And that's more or less how it looks like on a very high level. So we have the boot ROM, it's PBL, Qualcomm calls it. There is, after that, SBL, and after that, U-boot starts. We can also see that there's QSE. We'll talk about that later. And after that, Android starts. Unfortunately, as I mentioned, there is no intended shell anywhere which can be used, so that's unfortunate. We cannot really investigate anything there. So the approach is to focus on those targets. So it's always nice to look into possible recoveries. So maybe there's ROM recovery or there is U-boot recovery, which gives you some debug features which you can use to attack the device and get access to the internals. Or maybe focus on the early SBL stages of Qualcomm boot, which also can be useful because then we can investigate the system further. Focusing on Android was not really interesting because it's Android 13, very modern, and Google makes it, and they more or less know how to do it. So it's really not an easy target to focus on. So let's see if U-boot is any easier. So first of all, if you ever looked at U-boot, you might have seen this message. It says hit any key to stop auto boot, and it gives you a debug shell. You can see, unfortunately, the number after that is 0. So if you hit any key or press any combination, it doesn't really do anything. It ignores it. And U-boot is open source, and Google also released GPL code. So you can see what they modified there as well. So you see, if the boot delay is 0 in the while loop, it will ignore the whole while loop and it will never get in there. So the whole debug shell is disabled. So unfortunately, that's not an easy way in. But just before that, in the U-boot message, we can see the warning. It says, a warning, bad CRC using default environment. And that's already interesting, especially because the U-boot binary contains the default environment in the strings, so we can see that is actually used, but it's quite interesting for an attacker to see what's the eMMC initialization happening, and after that, what the CRC environment trying to be retrieved. So luckily with source code, we don't need to do too much reversing. We can see exactly where it happens. And what's going on is that when the device boots in the U-boot, it will try to read from a partition and get the U-boot environment from that partition, compute CRC over it, and if it's computed correctly, use that, and if not, default to the hard-coded environment. Well, can we do something about it? We need to look into eMMC for that. We can chip off the eMMC from the device, read it out, and see what's going on there. And if you take a look, from the U-boot binary, we can see that the partition from which environment is being retrieved is app SBL environment, but this partition is not on the device. It's just not present there. And of course, we can try the most simple thing, just create the partition. There's no free space on the eMMC, of course, but you can see the cache partition is not 400 megabytes anymore. It's tiny bit less, so we just take a chunk out of it, and it still works properly, so no issues there. And create few more partitions. The ART partition is also another one which is red, so it's also created by me just to test it. And we have these two partitions. When we put there the copy of the default environment and compute CRC correctly, we see that this message disappears, so it doesn't anymore print that using default environment. It just continues to boot. So we have full control of the U-boot environment there. And that's already quite a bit, but we need to get code execution there. So the most obvious way, of course, is to change boot delay. You've seen it's been set to 0. If you set it to 1, maybe hit any key and get the UART shell on U-boot. Unfortunately, that doesn't work because the code for the interactive shell is fully compiled out. So it looks like they try to prevent this from being exploited in the field. So it's not that easy. But still, if we look into the U-boot environment, that's how it looks like. We have some boot args, we have the boot delay here, enough to have the boot command. And the boot commands are still present, and they can be executed from this boot command parameter, but we cannot call them interactively. And these are standard commands. They're present in all the U-boot in many devices. So you have some boot commands, you have the device tree commands, there is run, go, which just jumps to wherever you want. There is CRC, computing CRC checksum over random memory, which you select. Memory display and memory write are of course, the most useful for an attacker. So we have all these commands available to us. We still need to bypass all the software mitigations which are listed on this slide. There is no software mitigations. Like there is no XN, there is no ASLR, there is no cookies, and especially XN and ASLR, the most useful because we don't need to know the offsets. We can just know where to write. And so that's trivial. After that, we can write anywhere in the code of U-boot itself, modify it, jump to anything we want, get code execution right there in U-boot. So it's one of the secure boot stages. So that's already good. We can report it to Google, and they clearly care about it. But of course, as an attacker, we would like to investigate the system further and get as much as possible out of it. So what's happening is the Android kernel of course, stored in the boot partitions. There's boot A, there's A and B slots. And U-boot verifies the U-boot Android image signatures. And we can easily patch the Android kernel in the MMC because we can modify it now by desoldering or modifying in place. And all we need to patch in the U-boot is just the signature check. It's one if, so we can change it to, for example, here to compare with itself, and that's good enough. And after that, of course, we need to do all the patching for Android image properly, but when it works, we have the root shell on the device, and we have SE/Linux disabled. So that was the first issue on the device, which was shared with Google, and they released CVE, so it explains exactly what's happening. It's unauthenticated partition being handled, and it allows compromise the device. So what can we do next after this? We can try to look into all kind of networking stuff on the device because we have the root shell, it's unrestricted, we have access to everything, we can debug, we can reverse, and so on. We can try to find bugs to get an RC, which would be definitely a good way to go. We could maybe take a look into Wi-Fi and BLE chips. There are some firmware installed on the file system. Maybe we can upload them. We can talk to the devices which are connecting to it. So it's also a possibly interesting attack path and maybe some future research. But for this one, I tried to escalate privileges even further. So although we have root shell and we have SE/Linux disabled, I mentioned in the beginning there is also QoC, and what it does, there is the chip is TrustZone enabled, so it can run in non-secure and secure world. So there is a separate operating system running next to your Android in the secure hardware mode, and it can run some applications. And during boot, we can see that there is single application which is present on the system, and it's being loaded during normal boot and then being used. So that was my next target to investigate. We can see that there is a few files. One of them is client.key and another one is parent code. They are still not readable. You can see the parent code is just some random bytes because it's encrypted, and it's encrypted in the secure world. So even though you have root, you don't really cannot get this data out because you don't have access to this in hardware. It's prevented. So I got the trusted application. It's stored on the file system in a proprietary Qualcomm format, but it's been reversed by somebody before, so I can convert it eventually to ELF. It's plain text. You can reverse it a little bit. And that's how it looks like. It has only a few commands, maybe 6, 7 commands. And one of them is OTP decrypt. What it looks like, there is OTP.package file, which can be uploaded to the device. It's uploaded encrypted, but then you can pass it to this TA, and the TA will decrypt it for you and then use later on. And it uses the parent code file for this. But you can see there's 2 issues in this single line of code of the unwrapped data. First of all, the destination buffer of the decryption is the response buffer, and the size is never checked. And we can use these 2 issues. The first one, when the data is unwrapped, it's going to be stored in the shared buffer. And this shared buffer is accessible to Android side. So since we have our client running in the Android side, we can just read the shared memory and see what they unwrapped this parent code to. And from what I looked into the binary from the reversing, it doesn't look like it's needed to be shared with the Android side at all. It only used internally and used to unwrap the next package after this, so it looks like just a wrong use of the destination buffer. And the second one is the payload length, and the payload length is not verified. So, and it used eventually, when it processes the whole command entirely, it goes to copy the data out, and it copies as many bytes as you ask it to copy. So we can, first of all, get the parent code out of it. You can see in the beginning, it's the actual code used by the device. And after that, we can copy the bunch of data from the TA itself, which contains various pointers, and other stack information from the device. So that was the second good thing, and that was reported as well to Google, and they issued another CVE for this finding. So why do these bugs matter? So Google did allow for hardpwn to have physical attack scenario, and it doesn't sound like the most realistic. That was in the beginning. Like, you're not going to have an attacker who breaks into your house, most likely. And if there isn't such an attacker, it doesn't really matter probably for you because you have bigger issues. And the possible reason why this can matter, because we can take a look now. For example, if we had an RCE on the device, remotely getting code execution, and we get root code execution on the device. After that, when the device is rebooted, we don't have our root code execution anymore as an attacker, and we would need to exploit this vulnerability again. So we wouldn't have a persistence on the device in this case. But if you have root privileges on the device, instead of using the physical access to the device and the MMC reader, we can just directly read-write to the partitions on the device. So all these modifications which were done physically could be done remotely if you have root privileges already on the device. Of course, it takes another vulnerability, but the moment you have it, you cannot be removed from the device. You're persistently going to stay there. So all that's needed is, well, easy first part, you just get RCE. And after that, you modify the block 0. It has the GPT partitions. You create these 2 new partitions. Oh, well, actually, one is needed, the SBL app environment. You specify that there is another environment partition in GPT partitions. Then you put the correct environment, just like we did, compute RC properly. And next time when it boots, it will always use your environment. And after that, whatever you boot, it cannot be trusted because you already got code execution in your boot. So they cannot really patch it easily. So that's pretty much it. It was quite easy and straightforward eventually once all of it is figured out. But now I'll try to do a demo. And I don't have a video, so if it doesn't work, you know it's all faked. It's going to take a second, unfortunately, because I need to connect to the device. I guess you don't see what I see. I don't see what you see. Now you see the terminal. Maybe I can make it a bit larger font. Or not. I have no idea where it is. This one? Perfect. All right. So what I'll try to show is that this is the device. I don't send any commands to it. It just, in the state it is. It could have been from the physical modification in this case, or from your RC after you modified all these partitions. And when it's booted the next time, it starts with initial log, and you can see it prints the string arbitrary code execution because we have persistence on the device. After that, what I implemented just for the sake of investigating deeper, so they don't have the interactive shell in U-boot because it was compiled out. So I implemented in my shell code in the U-boot environment. So that's the only NAS device which has the interactive U-boot shell. That is it from me. If you have any questions, I will be happy to answer them. And if you have questions later, we can also discuss.
You're a lovely audience. You're clapping without even being asked. Thank you. Do you have questions? Please ask some questions.
Hi, lovely presentation. Thank you for it. So I had a question, and I think I might have missed it, but you said this is for Android 13 or Android 14 as well?
It had Android 13 at that time. I'm not sure. They might have updated as well in the new update, the Android version. I do not remember for sure.
Do you have any questions more? Yes.
Thanks for the presentation. Could you estimate the time you spend on that?
So Hardphone itself starts on Monday or Tuesday of the week of the conference, and it finishes with the last talk of the conference. But Google added 2 more weeks to write up the exploits, make them more or less properly working, and submit the last bugs. So there was in total 2 weeks of effort for this, more or less.
All right, thank you.
My question is, how much time did you spend during this? Did you sleep during these 2 weeks?
Not at all. Not at all.
All right. Any last question? No. Perfect. Let's give a last round of applause to our last speaker of the conference. Thanks, Sergei.